There was a question came up. You saw a video on friction welding, and friction welding is used in very critical parts. Actually, you may not have gotten to that part of the lecture and the other parts, but they put together rotor forgings for aircraft, and you can take two $40,000 parts and turn them into a $70,000 part by, or two $30,000 parts and turn them into a $70,000 part by welding together, or you can turn them into pieces of scrap by welding them together. Okay, but anyway, this is a friction weld. This was done in a laboratory. It's just two 1-inch bars of steel, and they just hold one stationary and spin the other one, ram them together, and it heats up. And you saw the video of friction welding. I guess Greg said that company's no longer in business, but anyway.
All right.
There was a question last time about submerged arc welding, so actually this is a picture of some submerged arc welds on a large gantry, and I thought, gee, that looks like a pressure vessel. And then I looked down here, photographed courtesy of BAE Systems, so it's probably part of a submarine hull in Britain. Okay, it's probably a titanium, not titanium, but a British submarine hull. Okay, that's not the way we do it, but the Brits probably weld by rotating the whole cylinder. Their subs aren't quite as big. We basically stand it on the end like a cup, and we make vertical welds. Anybody know why we make vertical welds rather than flat position welds when we're welding the hull? Because you can make 4 at a time rather than just one. When you're doing this, you can basically make one as you rotate. But when you stand everything vertical, yeah, it turns out you have 4 seams. Or they make 4 seams. They may have more seams than that, but they basically take 4 quarters and put them together. And if you can weld 4 times, four seams at the same time, you get higher productivity than if you can only weld 1 seam at the same time. Okay, so if you go down to Quonset Point down here, you'll see they're welding vertically. Yeah.
Is that friction and stir welding going to increase mechanical or better the mechanical properties at all? I mean, like harden it or toughen it or anything like that?
Oh, friction welding? Well, that's not friction stir. This is friction stir.
Okay.
This is a friction stir weld in aluminum. You have a hard time with steel and high temperature metals with friction stir. Not to say people aren't trying it, but the problem is friction stir welding, you actually have a mandrel that spins and just runs through there, and it's just like an egg beater mixing solid metal, but it's getting warm by friction.
Okay.
But it doesn't actually melt, and that doesn't actually melt. If you actually melt these things, you actually end up getting hard spots where it quenches and things. It's an excellent process when it's running running correctly. They essentially used to make drive shafts for automobiles. You just no filler metal, just kind of put the parts in, set it up, let the machine run, and every 3 seconds you got to weld, just spin the weld out. Okay. Excellent process when it's running properly. When it's not running properly, it's an excellent way to make scrap. Okay, so it's just a question of getting things set right. But it's an efficient process, but it's limited in geometry. It's got to be basically circular. At least one part has to be circular. Okay, in a drive shaft, you got the yoke, okay, for your universal joint, right? But the other piece is just a round tube, and you can weld the tube to the yoke. The yoke is stationary typically, and the tube is spinning, but it doesn't have to be that way.
It just seems like when you're talking about stacking up basically the cylinders.
Yeah. Oh, you don't stack the cylinders vertically. You're just making 4 quarter sections into one big cylinder like this. Just take this and turn it sideways and weld 4 seams. Then you turn those horizontally. You ship them from Quonset Point to Groton, and now you put them together horizontally like this.
It just seems like you kind of open yourself up for a problem, where if you're doing each one individually, then if you have a problem, you can basically do that. But if you take 4 pieces, you weld them together, and then you find out your middle piece.
If you saw the fixtures they have down there, you'll find there's a lot of fixturing. They spent $100 million back 25 years ago to build this facility. So the fixturing holds everything together. Plus, I mean, I've never told me this, but I suspect you can get better circularity when you're welding vertically, because you don't have gravity trying to screw you up, okay, when you're rotating this big heavy thing. And the thing's going to turn to, gravity's going to ovalize that. But the British subs don't have the same types of requirements that we do.
But that's not done by hand, is it?
No, it's done by submerged arc, and I was going to show you a picture of that. Okay. This is submerged arc. This is what we think Roosevelt was writing to Churchill about. It was invented in 1936 by Union Carbide and was called the Union Melt process. But basically you have two heavy section plates and you put a little V-groove in here and you feed a wire through here, but you have sand, a flux, it says flux shelf, but basically the flux, you just pour it on there like sand. It's a $3 a pound sand, okay? It's not what you want to use for your kids. Oh, well, there's nothing wrong with using it for your kids' sandbox. It's not particularly toxic. But it's submerged arc because the arc is actually underneath the sand. You can walk by this, nothing on you. You'll see every now and then a few little bubbles of gas pop through, and you'll hear the thing kind of sputtering a little bit. You can tell that an arc's going on, but you can have anywhere from 500 to 2,000 amp arc and put in huge deposits. But the problem is it only works in the horizontal position, which is why they can show you this picture and you can get very high productivity welding, but only one weld at a time at the 12 o'clock position. They rotate the whole cylinder. You can't go vertical. If you're doing gas metal arc welding, you may only be using 200 or 300 amps, sometimes 400 amps. You don't have a flux to contain all the weld spatter. We can talk about that later.
So is the wire actually melting?
Oh yeah, the wire's melting. You're feeding that wire down through there fairly rapidly. I mean, you can see the wire feeding in kind of like that speed. You're melting very quickly. You can lay down 60 pounds an hour with this process, whereas a guy welding by hand might lay down 3 or 4 pounds an hour.
And does that affect the, I guess, strength of the material now that you have this?
If you're welding really high strength steels, this probably puts in too much heat, lower it, and softens the steel, which is another reason. Although they do it for HY80, they do it for HY100. I don't know they've ever developed it for HY130.
What is it? Is that wire that's running through there, is that made out of the same material?
No, it's got a special formulation. It's more highly alloyed, so that when it solidifies, the high strength steels get their strength from heat treatment. You're not heat treating the weld metal, you're making a casting, but you add alloy to it. In fact, that's one of the problems with the Seawolf submarine. The wire was on what they call the high side chemistry. Everything was on the high side of manganese and silicon and everything else, and it was too highly alloyed. They thought they were welding HY100, and in fact, the weld metal was actually HY130. It was too strong, and therefore they got hydrogen cracks. So, I mean, you have to, there's a lot of work, in fact, that goes into developing a wire and a flux that goes with a particular steel. The Japanese in the 1980s, when their steel companies and their shipbuilding, commercial shipbuilding was doing so well, those steel companies would develop special wires, special fluxes for a given steel plate, and the steel company would sell you the package, okay, of how to weld this new steel they had developed. Whereas over this country, the people who develop gases and fluxes for welding tended to be, or fluxes and wires for welding tended to be Union Carbide, Air Liquide in France, which is also Canadian. Well, anyway, a number of Airco, the gas suppliers. They wanted to sell gas for welding, so they would develop welding electrodes. But they didn't work with the steel companies. In Japan, it was sort of the steel companies developed the wires, the fluxes to weld the steel so they could sell the steel. Just a different marketing, and the Japanese system ended up giving a better integrated system, and the shipyards were getting fantastic productivity rates because the steel companies were developing welding consumables for them in order to sell the steel. Well, the steel is a lot more valuable than the gas, okay? So there was just more money in it, and so there was a bigger incentive. Does that answer your question? So that's submerged arc welding.
Now the flux reusable?
In theory, but you have to be careful. The flux is reusable in carbon steel. Sometimes people grind it up. Some people, well, people typically do filter out because you melt the flux and it turns into a slag, which is this glassy mess. And you certainly can reuse the unmelted sand. Okay, so they filter that out, reuse that at $3 a pound. In really cheap shops, they may try to grind up the slag and reuse it, but there actually are chemical reactions that go on, and so the slag, even if you grind it up, doesn't have the same chemistry. I'm not a big fan of reusing flux. If you go to there are some other processes. You can do submerged arc welding of nickel alloys. My very first contract in 1977 here, as a young assistant professor, was submerged arc welding of titanium for the Office of Naval Research. So this is 3/4 inch thick titanium, and these are submerged arc welds. And in order to, the Soviets had published a lot on this stuff, and Union Carbide had done it. Oops. And actually, there's 3 pieces here. These should go in the Smithsonian someday, I guess. They were actually, they weren't the first ones made. Union Carbide in their research labs had a contract from the Navy, but they decided this process was going to be too expensive, or not have a big enough market. I mean, how many titanium submarines was the U.S. going to build? And they were more interested in selling, stuff for steel. And it turns out their manager was my house tutor here. Had been my house tutor when I was a freshman. He told me about this. I went down and saw the Navy, and said, yeah, we're interested in continuing this work. So I ended up making some of those welds. Actually show some chemistry on there. Some of the purest welds. The Soviets had done it before us, but there was a little bit of literature. But we learned how to do it. But we had to take optical grade calcium fluoride. Titanium will react with any oxide. Molten titanium will react with any oxide. And you have to use fluoride or chloride fluxes. And fluorides tend to fume, and they're bad news. But the fluoride fluxes, in this case calcium fluoride, but calcium fluoride and strontium fluoride were the main fluxes. But we actually, in order to get the purity, we had to buy single crystal calcium fluoride at $100 a pound. These were just scraps from this place in western Massachusetts that was making optical crystals, okay? And we would grind it up into flux. But actually, I did an analysis, and it turns out to weld steel by submerged arc back then, you pay about, or you'd have about 4/10 of a pound of flux for every pound of weld metal, okay, that you would consume 40% as much weight of flux as you would weld metal. In titanium, you would consume 5 or 10 times as much flux by weight as you did titanium weld metal deposited. And at $100 a pound for the flux, we were talking about something that we did an economic analysis and told the Navy, forget it. Technically you could do it, but economically you couldn't. And that's what I said before. The whole Alpha Sub was not driven by economics, okay? And there were lots of problems with the titanium subs. But then, I think I mentioned, and this is this Electro Slag weld on titanium, and we said, I was at this meeting, and we were trying to figure out how the Soviets had built the Alpha Sub. This was like 1980 or 1981. And all of a sudden, it kind of dawned on me in this meeting down at David Taylor Annapolis, and I pulled a couple of people in the hall at the coffee break, and said, I know how they did it, I know how they did it. And then we came back and we made the first Electro Slag welds on titanium. Now, Electro Slag welding looks like this. Okay, this is the process to make an Electro Slag weld. And so you may have 2-inch thick plates that are vertical, and you use some water-cooled copper dams just to make a cavity. And you're going to make a casting basically and feed the wire straight down through here and pour some flux in here. Now in this case, the flux is molten, and you kind of build the whole thing with just a little bit of flux. A cup full of flux will make a 10 or 20 foot long vertical weld. So who cares about flux cost in that case? It's not like submerged arc where you're using 5 or 10 times the weight of flux as the weld deposit. So this was economical for fluxes, and in fact it works. This sample was actually made at the Oregon Graduate Center because after I demonstrated it could be done, the Navy classified it. Not that it needed to be classified, the Soviets were in the literature on it. All you have to do is go read the 1960s literature from the Soviet Union. But they basically classified it, and you can't do classified work at MIT, so I quit working on it. But anyway. But that's Electro Slag welding. It's used, well actually it was really developed at the Bataan Institute in the Soviet Union during World War II, and Professor Bataan, who was very powerful, used Electro Slag to rebuild German tanks, or not German tanks, but Soviet tanks. And he was credited with getting tanks back to the front and helping win the siege of, what was the siege? Stalingrad? Anyway, one of the two. Yeah. I mean, the Baton Institute's in Kiev, but I mean, he was a hero of the Soviet Union under Stalin, and a member of one of the 7 people of the Soviet Academy of Sciences that handed out all the research money. And so his son, who I think just passed away a year or 2 ago, but his son went on, and they were very powerful scientifically. And the research institute grew to 5,000 or 10,000 people in welding. It's the world's largest welding institute.
They took my back
Yeah.
shot.
Pardon me?
They took my back shot.
No, they didn't take it. They didn't know. He was a hero all the way to the end. I mean, both batons, P-A-T-O-N. It's called baton. Ukrainian, I guess. Anyway, they developed the submerged arc process, or the Electro Slag process, and the Soviets used to use it all the time. Not necessarily because it was a great process, but because they invented it. Yeah.
So on board, one of the samples you had, where you had the bead or whatever it was on the top, when you look at it, you don't see the V. Is that just that good of a
Oh no,
weld?
those are just bead on plate.
Okay.
It's such a pain to cut the titanium. Those are all saw cut. In fact, I did find one of my arc cut, my oxyacetylene cut of titanium. That's a titanium piece. You can see the quality of the edges. We don't have to talk about the gas tungsten arc welds on there right now, but I did find one. I knew I had one, and shows it's kind of a lousy cut surface, and you have to grind it all off because it's contaminated with oxygen and stuff. But it is a fast cutting process.
Just doing bead on plate welds, how do you determine the strength of the weld then?
No, we never did determine the strength of the weld because we determined it was too expensive to make. I mean, eventually we would have beveled the plates and everything, but cutting titanium, saw cutting titanium, it could take a half a day to cut a plate.
Suppose you did get to the beveled sections and would you do like a stress strain analysis to determine
Yeah, but I
the strength
mean,
of the weld, or?
there's enough literature on titanium that you know that titanium tends to develop full strength welds.
Okay.
Okay, in fact, one of the problems is got a little bit of oxygen nitrogen contamination. You get too high a strength of the weld metal. Okay, because oxygen is to titanium as carbon is to steel. It hardens it,
Okay.
it strengthens it. And the big problem in titanium is keeping the oxygen out. So the weld metal, you'll probably get good strength. Mechanical properties may not be so great, but titanium doesn't have great mechanical properties compared to steel anyway. And you guys will get that in the fracture mechanics section.
This is more just when they talk about like titanium washes and everything. How do they cut the metal for the washes? Is that why they're so expensive? Is it
Washers?
more, you know, just the washes have titanium, whatever. Is it more?
Well,
the
there's-
cost?
Well, titanium, they can laser cut the titanium, but you still have to grind the edges. You can also stamp titanium cheap, okay, with dies. You just cut it like scissors, great big set of scissors, if you will. I mean, it's not that you can't cut titanium; it's just a pain in the neck. Okay, but titanium's expensive because it goes for $50 a pound, whereas steel goes for $1 a pound. That's the difference. So no matter what you do, it's going to be expensive because the scrap is expensive. And if you cut some smaller part out of the bigger part, everything out of that rectangular bigger part that's not the part is scrap. So typical utilization in a shipyard of metal used to metal purchased, or what the Air Force calls the buy-to-fly ratio, okay, might be 2 or 3 to 1. You're only using 30 to 50% of the metal you buy because you're throwing away the edges that don't have the shape that you want. Okay, and you start throwing away $50 a pound material, it starts to get expensive. I mean, you're not throwing it away; you're reselling it as scrap. But as scrap, it's worth $5 a pound rather than $50 a pound. And that's the whole problem with nickel-based alloys at $100 a pound, and titanium alloys at $50 a pound. The scrap costs, the materials costs start getting severe. Okay. Yeah.
Can we simulate weldings in a computer? And if we can, how effective is that for new welding procedures?
Well, you can do anything. It depends on what level of detail you want to simulate something, okay, in the computer. And part of the problem, one of the reasons scientists don't like to work on welding, in fact, I was going to talk about this in a second, might as well talk about it now, is because welding is too complex for the average scientist, okay? And the quote I like to use is, a scientist is actually from Theodore von Karman. Anybody know who Theodore von Karman was? I always like to say he was the guy who explained why the Wright brothers were successful. He was one of the greatest American scientists and engineers of the 20th century. He was a professor at Caltech, which someday I'll tell you how Caltech's just a spin-off of MIT. It actually was founded by a former president of MIT who was frustrated with MIT. And they have same mascot, the beaver, same school colors. Okay, but anyway, and this guy's just was founded by MIT people. Anyway, Theodore von Karman has a quote. He says, "A scientist explains that which exists. An engineer creates that which never was." And I like the quote because scientists hear that quote and they think that's great because they like to think of science and create, explaining something. And so to explain something, you don't want to explain something that's very complex because you can't explain it. You can't write down the equations, right? An engineer likes to create that which never was. Well, when they want to create something, they don't care about whether they can always write down the equations. They just want to see if it works, sort of Edisonian sometimes. And engineers like the quote from von Karman. So von Karman was both a great scientist and a great engineer, and he understood the difference in the mentalities. But it's important to understand, scientists will redefine the problem so that they can solve it mathematically. And you guys are now learning about science at MIT and how you have to learn these mathematical formulae, right? But when you go back to work, you're going to be working as engineers. You're never going to solve a differential equation. How many of you think you'll ever solve another differential equation after these classes, right? But they're going to walk you through this for 3 years, okay? And they're going to show you what science is all about, okay? And you'll be able to explain that which exists. But that's not what your job is. Your job is to create that which never was, okay? And actually, Joel Moses, who used to be the provost here at MIT, and he'd been dean of engineering before that, he likes to say, and the Media Lab creates that which never will be. Okay? Which is a lot of truth to that, okay? The Media Lab's a lot of hype and not a lot of action. But I don't mind that being on the World Wide Web, because it's true. But in any case, where was I going with some of this? I remember in 1980, one of the big events in my career. I was still a young untenured professor, and the Office of Naval Research was interested in having someone at a decent school study welding and turn out welding engineers. And they had gotten a lot of money, but they didn't get any new personnel to manage this research money. And so the first thing they did is, in like 1979, they decided, they picked a guy at Penn State University who was big on sonar materials, sonar ceramics, and they gave him a big slug of money, like $400,000, $500,000, which back then was a small fortune. I mean, it was two or three times what a professor at a big school needed for research, okay? And it was just one slug, one big grant. And a lot of the improvements in sonar materials came out of that program. And then in 1980, or actually in 1979, I got a phone call saying, what would you do with $500,000 a year? I was the second person. They chose one person a year, and I was the second year. I was untenured, and so they were taking a risk. But in fact, that decision that was made without my presence, without my knowledge by some people in Washington, was what really got me my tenure and gave me my independence, so I could thumb my nose at all the administration around here for the rest of my career. Because I had more research money all of a sudden than any other faculty member in the department, senior or junior. And I had enough money to have, 10 graduate students and work on, I mean, I didn't have to write a proposal to work on electro slag welding of titanium. I could go do what I wanted because the Navy gave me this money and there was enough of it that I could do things. Well, and then that lasted for about 4 or 5 years, and I got my tenure, and that was nice. But then the Navy started cutting back as things got tighter, but I did have funding from ONR for 30 years. I finally lost my ONR funding because the new person who came in, I went through 2 different people who, one moved on to NSF and the other one retired. But then the next person who came in lost my proposal, okay? You lost my proposal? I mean, you can't keep track. Anyway, that's another story. But to get back to this question of complexity and what can you model and stuff, when I got this money, they wanted me to get other people involved, and some of you will get to know probably Professor Hart. Dave Hart over Mechanical Engineering was a brand new assistant professor, and he was one of the people I funded with some of this O&R money, because he was interested in doing some practical things. Now I went down to the spectroscopy lab here in the physics department and tried to get them interested in arcs and studying arcs, and they said, oh, we already know everything about arcs. There's nothing more to learn. And I couldn't quite understand that response, and this is when I was learning what it means to be a scientist, okay? What I learned is welding arcs are too complex for a physicist to study. The physicist can study two types of plasmas. A weakly ionized plasma, in which case, if you look at your thermodynamic system, almost everything is a neutral atom, and every now and then you'll have a charged atom, okay? But there's so few, when it's weakly ionized, like 0.1 or 0.001% of the particles are actually charged, so you can treat each charged particle as if it's surrounded by neutrals. And you can solve that problem mathematically, right? Because you have a single charged particle surrounded by a bunch of neutrals. Or, the problem they can solve, if this is weakly ionized, you go to the other extreme, which is fully ionized, where everything is charged, okay? There are essentially almost no neutrals, okay? That they can handle because everything's got a charge on it, and you can write down the equations for that. What they can't handle is something that's partially ionized, where maybe 5 or 10 or 15 or 30% of the particles are charged. And now you have a strong statistical problem of writing down your equations of what is the adjacent particle, is it charged or not? And the mathematics for that automatically becomes intractable. I mean, just immediately becomes bigger than any computer can handle. And that's why the physicist says, oh, that problem's already been solved. Okay, that's their approach to such a problem, is to poo-poo it and say, oh, that's not an interesting problem. It's not interesting because they can't write down the equations. Okay, so that was my epiphany learning about science and engineering. And so I give whole talks about physicists now, about how worthless they are. Okay? Not that they're not smart people, but basically they're sort of worthless. By the same token, I've learned over the years that some of the best engineering done at MIT is done in the School of Science. And most of the faculty in the School of Engineering are wannabe scientists. Okay? Only about 20% of the faculty in the School of Engineering at MIT are really engineers. All the rest of them wish they could be in the science department explaining that which exists. So when you take your courses from these different people, just kind of peg them early on, first 10, 15 minutes. You can tell whether you've got a wannabe scientist or you really got a real engineer, okay? And it's going to be about 4 to 1 ratio, okay? That's just the way it is. But they're all, one of the nice things about MIT, they're virtually all competent in what they do. And you won't find that in most other schools, okay? And that's one of the beauties of MIT. If I go and talk to someone and ask for some advice, scientific advice or information or whatever, they usually know what they're talking about if it's in their field. Or they're willing to say they don't know, okay? And a lot of other places, it's a bunch of fluff, people pretending like they know what they're talking about. Anyway, so I'm getting off that thing. This is what's called the Saha equation. And it turns out, if I just think of this little welding arc, here's my electrode, and here's my plasma, and here's my base plate, and I'm going to impose a current, whether it be 100 amps or 200 amps. I can figure out, as a scientist, what the mobility of the electrons are. And it turns out, this plasma, why is temperature not important? Because nature will choose the lowest possible temperature to generate enough electrons to carry the current that's imposed by the power supply. If I put 100 amps through this, the plasma will be ionized sufficiently that I have enough electrons to carry 100 amps. If I want to put 200 amps into it with the power supply, it will increase the temperature by maybe 100 or 200 degrees. I'll show you on this plot in a second. It doesn't take much of a temperature difference. Out of 10,000 degrees, another 100 degrees could double the number of of free electrons, okay? So you only need, just the system wants to come to its lowest energy level, and the lowest energy level will be the lowest possible temperature to give you enough electrons to generate the current that you're imposing on it. So the power supply is determining what the current is, and the plasma is just responding to generate enough charged particles to carry the current that you're imposing. Okay? So this is a Saha equation named after an Indian physicist, okay, from the 1920s. And it's particle density versus temperature in thousands of degrees Kelvin. And this curve is actually, this is for argon. This is NT, which is total number of particles. Okay, I've been calling neutrals or particles N's. That's kind of what the plasma physicists do. And this is just a hyperbola. In this hyperbola, particle density is kind of 1 over pressure for a gas, right? The higher the density, or actually, no, it's equal to the density. And particle density is equal to the pressure, it's proportional to the pressure. So this is basically pressure and temperature. And for an ideal gas, in your high temperatures where you have a reasonable distance between particles, you basically have the ideal gas law. This hyperbola is PV is equal to nRT. Okay, where N in that case is number of particles. Okay, so that's the total number of particles, and the number. Well, if you have pure argon at low temperatures below 5,000 Kelvin, essentially argon, A, this A line, which is neutral argon atoms, is equal to the total number of particles. That's all you got in your gas, is pure argon. However, as you get to around 11,000 Kelvin, according to this calculation, some of the argon will be hot enough, you'll start to strip off some electrons, and you now have argon ion line, this is A+, and in fact that is exactly the same thing as N sub E, number of electrons, because, you know, every argon ion you get 1 electron initially when you're singly ionized. So this thing is coming up, this is orders of magnitude here, okay? 10 to the 14th per cubic centimeter up to 10 to the 17th. And so the thing's starting to ionize. As you get higher and higher in temperature, you'll start getting doubly ionized. And now the number of electrons spins off as more than the number of argon atoms. And so these two curves of number of electrons and argon ions are no longer the same line. And you get triply ionized if you get up here to 35,000 Kelvin. Well, that's not where we're interested. This is just a calculation of ionization for argon. And they have these types of plots in the plasma physics literature for nitrogen and oxygen and air and carbon dioxide and things like that. But basically it's just showing you what the particles will be at a given temperature. Now if I go back and look at the mobility of the electrons in here, I can calculate that in order to run typical welding arcs, I need between 5 and 30% ionized. Okay? That is not weakly ionized. It's not fully ionized. It's a partially ionized plasma. Okay? The physicists don't want to touch this with a 10-foot pole. They'll much rather work on tokamaks and things like that. Tokamak is a fully ionized plasma. I mean, in tokamaks, you're trying to get out of here where you strip all the electrons off. Okay, hundreds of thousands of degrees or millions of degrees Kelvin. You're going way out here. But this practical area back here for welding, no one wants to touch. Well, where is 5 to 30% ionized? Well, 5% ionized would be when 5% of your gas is argon ions and 95% is argon neutrals. So that would be somewhere around in here at about maybe 11,000 degrees Kelvin. And 30% ionized might be up here at maybe 12 or 13,000 degrees Kelvin. And if you go measure the temperature of an argon arc, guess what temperatures you get? Well, 11 to 12, 13,000 degrees, depending on the temperatures you're using. Now, it's not absolutely uniform. In fact, the highest temperatures are up here, and you can plot, and you can calculate those temperatures today. Within the last 15 years, we can do excellent calculations of what's happening in this plasma. And within the last 10 years, we actually can talk about how that plasma interacts with the surface here, which is something else we're going to talk about today. So I'm actually getting back to your question. Can you model this? Okay? I couldn't 25 years ago really model what happened in a real plasma. In the 1920s, Saha had developed this plot, which assumed absolutely uniform temperature, and everything in actually pure gas. Today, we can model impure gases with computers. We can model temperature gradients, so we actually can model this. We now have gotten to the point where we can model a little bit about what goes on as it interacts with the surface. We've gotten to the point where, with completely different models, we can model the convection in the weld pool. We might talk about that in the next few days. We've always been able, for 30 or 40 years, to be able to model the heat flow that goes on. We do not have computers big enough, and probably will not for another 50 years, to model the residual stresses as this thing cools down and stuff, the elastic plastic, because that's a coupled thermomechanical process with nonlinear properties of the materials and temperature-dependent properties of the materials. And you start talking about transient, thermomechanical, nonlinear, all these things that the mathematicians over here would love to come and start talking about how we can improve our modeling techniques. So can you model the welding process? We are at the point where we can model pieces of the welding process right now. And about 10 or 15 years ago, there was a scientist at Sandia National Lab who sold Sandia a bill of goods to spend millions of dollars a year to model the welding process. Sandia is the laboratory in Albuquerque, New Mexico that's responsible for nuclear warhead safety. And they have to weld nuclear warheads, and so they're interested in welding. They actually have a very good welding group. But this one person said, went to the management and told the management, we can model the welding process. Computers are powerful now that it's 1990, okay? And we're gonna model the whole process and do an integrated thing. And went out and got people from other DOE labs around the country and just pissed the money away, okay? Because anybody who actually had done modeling on the little pieces knew that we're nowhere, even today, we're nowhere near. And certainly in 1990, the computers weren't big enough. Does that answer your question? A long answer that gets into the politics of what it is to be a physicist, right? But the creativity in welding is knowing how to simplify the problem, to make it a tractable problem, okay, without losing the essential physics. As Einstein said, although he wasn't the first person to say it, it's actually an old Yiddish proverb, as simple as possible, but no simpler, okay? And too many times people model things and they oversimplify it. And I gave you the example that one of the first days I brought in these pieces, brazed pieces, these honeycomb type of things were from the internal intercooler recuperator, with just a great big heat exchanger the size of this room that was going to take the hot gases going up the stack of a diesel, powered destroyer or something, and they were going to recover the heat and preheat the air that's coming in, so that you get, at low speeds you could get a 5-fold improvement in, efficiency because of things. And that was going to be more time on station in the battle group and stuff, because they didn't have to come back to the carrier. I told you about some of this stuff. Well, that was in the early 90s, and it was too complex to do a mathematical model. They could have done it. I mean, if they were building a space shuttle, they could have done it. But they wanted to cut the cost. This was when peace was breaking out in the early 90s. And the budgets were tight, and they decided to just do a 2-dimensional model of gas flow through this heat exchanger. And I told you that the problem is no one told the gas it had to go through symmetrically, okay? And so it heated up one side more than another side, and the whole thing within 2 minutes twisted like a pretzel. Big pieces of steel, 6 inches in diameter, just like it was a piece of cooked spaghetti, because of the thermal stresses. I mean, they could have modeled that properly back then, but it would have cost probably $1 million or more worth of modeling. They decided to do the $50,000 or $100,000 2-dimensional model as opposed to the full 3-dimensional model. So when you get to this question of modeling, real processes are too complex to do what you really want to do, okay? But what you have to do is be clever enough to say, well, what are the essential elements? And then you can model that. So that's a very long-winded answer, but it's a much more profound question than maybe you understood. Okay, it was a good question. Okay, so I did want to tell you about that. I also, any other questions on any of that? Now, if we talk about, we have this anode boundary layer down here. We want to get heat. I mean, for welding, my purpose is to try to get heat into the workpiece so I can melt a weld pool and do my welding. But I have a problem with this anode boundary layer. We talked about the electrons carry 80 to 90% of the heat to the anode is carried by the electrons in the argon arc. We also talked about welders have short-term health problems, primarily bronchitis. I didn't mention that yesterday, but there have been big epidemiological studies. The biggest that I know of was done at Caterpillar about 15 years ago, where they took almost 5,000 welders in Peoria, Illinois, and 5,000 controls, office workers and others, so they all lived in the same community, and they did a huge epidemiological study that Caterpillar paid for. And the outcome of it was they could show that the people who were actually on the shop floor welding got bronchitis. They got colds more often in the winter and in the summer. Why? Because their lungs were full of all this dust. And if you did x-ray scans on them, you could see the iron in their lungs, and it's something called siderosis. If they quit welding, people have done studies, it takes about 10 years for those macrophages to clear the lungs of all that iron after you quit welding, so that your lungs look as clean as someone who isn't working in a dusty environment all the time. But if they looked at cancer and all these other things, they could not show that the welders had any higher incidence of any other types of diseases. Okay? The only thing they could show was short-term bronchitis problems while you were welding, and then it took about 10 years after you quit welding to clear your lungs. Now, they have to do some other things when they do these things. They have to account for the fact that welders tend to smoke more than the average of the population. So if you actually, there have been studies early on where people said, oh, welders have more cancer than others. But then someone came along, some physicist, not physicist, health physicist or industrial hygienist comes along and says, well, why don't we take into account of the fact whether they smoke cigarettes more? And if you do that, you find there's no difference. So if you take in that compounding effect of smoking, you find welders get no more lung cancer than anybody else. Okay. So a welder who doesn't smoke is just as healthy as any other office worker, basically, except they'll get more colds in the winter and some. Okay. So we kind of got off on that tangent, which actually is not too much of a tangent because you would have gotten it about 2 or 3 lectures later. We just kind of took it out of order. But anyway, getting back to the boundary layer here, and we said the electrons can punch through, and because of that, about 80%, 90% of the heat goes through by the electrons essentially defeating the boundary layer. Now there's a paper by Demishku and Fender in 1980 in the Journal of Applied Physics that actually talks about 4 different boundary layers. And this is not something you need to know, it's sort of cultural. So the next time you're at a cocktail party, you can say, well, have you thought about the recombination of mean-free path? Okay? And if you need a little more room, people probably walk away. So the recombination of electrons and ions turning back into a neutral atom. So we're talking about, I got an electron and an ion could recombine and form a neutral ion. And what's the distance in a 1 atmosphere plasma for that to happen? And that's on the order of 0.3 to 0.6 of a millimeter. So that you can think of the boundary layer as being something on the order of a few tenths of a millimeter thick in terms of this boundary layer that the electrons have to punch through, which forms the anode boundary layer. The energy exchange mean-free path, which is the distance the electron travels to thermalize. And remember, the electrons are more mobile and they accelerate in the electric field faster. They have about 100 times more mobility, and therefore they bounce into these neutrals or these ions and transfer their energy that they picked up. It turns out that's about 0.2 of a millimeter. 0.2 of a millimeter is only about 0.08 of an inch. Okay? The electron mean free path for elastic collisions. How far does an electron travel before it runs into one of these other guys? And that's about 10 to the minus 3 millimeters. Well, there's about 100-fold difference between these two numbers. And if you know anything about random walk kind of billiard balls bouncing around in each other, how many collisions it takes to go a certain distance, the number of collisions goes as the distance goes as the square root of the number of collisions. So you can estimate right now that it would take something like 10,000 collisions of that electron before it gives up all its energy. Now, as it's doing that, it's picking up more energy, but you can kind of say that, you know, it doesn't, and, well, why would it take 10,000 collisions? Anybody think of a reason? If you think of an electron that weighs 1/1839th of a proton or whatever, right? And the ion is a number of protons and neutrons and stuff, and they weigh 20,000 times as much as that electron. It's going to take a lot of collisions because the maximum energy momentum transfer is when the two particles are equal in weight. And these two are not equal in weight. That electron tends to elastically bounce off those big heavy atoms, and it's hard for them to move them. But after 10,000 collisions, the electron will have given up all of its energy. So that's kind of another characteristic dimension down in this boundary layer. And the last one is called the Debye screening length, and it actually is a complex formula of pressure. This is density of particles, so this is pressure. That's the Coulomb charge again. This is permittivity of free space. It's about 10 to the minus 5 millimeters of 1 atmosphere. And the Debye screening length is over what distance can another atom see the charge on that electron or that neutral. Okay? Electrically, can they detect each other? And they hardly see each other, except over those types of distances. So there's lots of types of things that are going on here. So getting back to when I told you that 15 years ago or 20 years ago we could model what's going on in the plasma, and 10 or 15 years ago we got to the point where we could actually model what's going on in here. In 1980, we couldn't model what was going on here. These guys were just kind of giving us order of magnitude calculations for the processes that are going on here. To actually model what's going on in that boundary layer, it's probably only in the last 5 or 10 years we can actually model all the different types of collisions and things and forces of attraction and everything between these particles.
These layers are distinct, one.
No, they're not distinct. And basically, they're just distances within this boundary layer. If you want to think, what's the thermal boundary layer, which is the one that kind of controls the heat transfer, it's either this one or this one. Okay? Because when the atoms recombine, they give up energy. So that is sort of a thermal boundary layer. And this is thermalizing. It takes that much travel distance before the electrons will have imparted their energy. So these are the thermal boundary layers, but these are other characteristic distances that, depending on what process you're talking about, have some significance. Okay? So when you try to start simplifying things, you have to very well define what question are you trying to answer. Okay? Am I talking about the distance over which particles see the charge of another particle? Well, then it's a very small distance. If I'm talking about a thermal boundary layer, it's something on the order of 0.2 of a millimeter, like 10 or 15 thousandths maximum thickness.
So what happens, the electrons from the plasma hit the surface of the metal?
Yep.
And then
Well, they have a Thomson energy, 1/2 MV squared, just because they're at 10,000 degrees.
And
that's equivalent to about a volt. Then they're accelerated across here. This is sort of a rarefied space charge region. I mean, this is mostly neutrals. There's not enough electrons in here to carry the current because it's cooler. It's only 3,000 degrees. It's not 10,000 degrees. Go back to Ellen Boss-Heller. Okay, if I go back to Ellen Boss-Heller, at 3,000 degrees, let's do Ellen Boss-Heller, right set up. At 3,000 degrees, I don't have any charge carriers. Okay? So the electrons have to punch their way through that thermal boundary layer of 10 or 15 thousandths. To do that, they have to pick up a big voltage, a big electric field, and that energy gets deposited in here. But in addition, they decay down to the Fermi energy of electrons in the metal. And that's this whole heat transfer that I talked about yesterday. where we have the electrons, every electron is carrying energy. So it's the current times the Thomson energy, the hot gas, and 1/2 MV squared in the gas energy, because they're going to be moving a lot slower down here, or at much a lower temperature, and therefore moving slower. The anode voltage drop, which is coming across here, and then decaying down to the energy level of all the other electrons, that's how much heat is given off by the electrons coming through here, which is 80 to 90% of the total heat getting to the surface.
So they are absorbed by the metal.
They're absorbed by the metal. But I can break that absorption down into their energy transfers by three different processes.
So we are increase the current inside the metal. The metal is more negatively charged.
No. You've got to maintain electrical neutrality in here. You start building up just a few extra electrons, and you've got charges that'll strike arcs from here to the sun. Okay, you get huge voltages if you have any imbalance in charge. So electrical neutrality is one of the things you have to assume when you do all of this. But the electrons condense to a lower temperature state, if you will. And they give up all the heat of being at high temperature and having been accelerated across here, and then condensing. That's all given up to the metal as heat in the metal.
So it just ground the metal.
Yeah. But this is the physical process. These are the three physical processes by which heat is transferred by those electrons to the metal. Now, you also have hot gases coming across here, and just like any hot gas going across the boundary layer, you have conduction and convection and radiation across that boundary layer. But that's only 10 to 20% of the total heat. It's not a lot. Okay? And we know that's true. I'll do this finally. We know that's true because you can look at, and I couldn't find the plot. There is a picture kind of like this. It looks exactly like this, but I couldn't find it in the Welding handbook. If I have a plasma arc, we talked about plasma arc cutting. If I have a plasma arc and I do not transfer heat, current, but I had it's not this arc, okay, but I didn't transfer the current to the workpiece, I would end up melting a very shallow weld pool. If I actually have a plasma arc where I actually carry some of the current into the base plate, I will do much more efficient melting. Now this one is actually showing the difference between a plasma arc welder where I have a jet burner, where I have a huge, very strong jet pushing the surface aside and whatnot, and this one, which is just a gas tungsten arc, and I form a shallow weld pool. So this is a jet burner, this is a pre-mixed flame, if you will, arc. But you get the same type of behavior. You'll get about 2,000 watts per square centimeter in a non-transferred plasma arc where you don't have any current going to the workpiece. If you do the exact same thing and most of your current is going to the workpiece, you'll get 10 to 20,000 because you got 90% of the heat carried by the electrons. You'll get 10 times more heat transfer when you have those extra electrons carrying the heat into the metal. Okay? And you can actually run that experiment between a transferred plasma arc, which is a lousy cutting machine, or a non-transferred plasma arc, and a transferred plasma arc. You can heat up ceramics, no current going into the ceramic, but it's only like a very good flame. But if you actually carry electrons into the metal, all the heat of those electrons gets deposited in the metal, and it's 10 times as much heat as you would get from just a hot gas blowing on the surface. The electrons are carrying the heat. And that's why current is important in heat transfer of arcs, and voltage is not. Okay? Current is what determines the heat distribution on the surface. Okay? So I'll see you on Monday. Enjoy your quiz tomorrow.
Tuesday.
It is Monday, no, Tuesday. I'll see you on Tuesday. Yeah.